So Jasmine asked me to make a short video describing the project that I did for this course. So I'm going to do that. Yeah, what I did was I formalized an existing mathematical proof. I took one from a maths course, a measure of theoretic probability, and I just took one of the first theorems in the book, and I just formalized this proof. So this is the theorem. Let I be this set of intervals, then this sigma I is B, and I translated that into lean. That's here. So the sigma I, that means that we generate measurable space from this set I, which is described in lean by range IIC, and then B corresponds to the Borel algebra of R. So that's the way this works. So now we've translated the theorem into lean, and what I then did, I went through this proof and tried to apply every step in lean. So the first step is really neat. You can just the proof says we prove the two obvious inclusions starting with sigma I is a subset of B. And that just corresponds to the command in lean apply LE anti-sim, where we say, okay, I'm going to prove both inclusions. And then because, and since both inclusions hold, they must be equal. That's the idea. And so first I proved this inclusion. And that's only the proof of that in the lecture notes is only one sentence basically. It starts by saying since this thing is equal to this thing, and this thing is contained in B, is an element of B, we have that I is a subset of B, and then also sigma I is a subset of B. Also, this equality is like easy to see for mathematicians that this is true. Because this 1 over n, it tends to go to 0, and that tends to 0 as n goes to infinity, and that's why this equality holds. But I actually needed to have a separate lemma to show that this is the case, because mathematicians have this as working knowledge, basically, but then, yeah, this is still something that you need to tell lean. So I don't know if there already exists theorem for this in the library, but it's also quite hard to find out if such a theorem already exists, because there are some techniques to search the library, but in the end it was also worth it for the experience of proving it. And then this I showed that this thing is then contained in B because it's an infinite intersection of things that are contained in B. And then you can see that I do that here with apply is measurable.inter, where I say, okay, for this to be in B, like I can just prove, it suffices to prove that each of these things is in B. And that's how I go through this proof. And then there is also a proof for the reverse inclusion, which does some observations. This observation is that it's an infinite union, and that this infinite union is contained in sigma I. You can see these steps basically happening here. This is this infinite union part, this equality, and then this part I prove that this union is then contained in sigma I, and that is the case because of this this definition or theorem that says that a union is measurable if all of the elements of the union are also measurable or are also measurable. So that means that showing that these things are all in sigma I is sufficient. Well, that's what I do here, because they are by definition they are. Then there are, the proof continues. Knowing this, we conclude that this this difference between sets is also in sigma I. So that's really similar to what we earlier saw. And you can see that, like, it's not just these steps I need to write into the proof, but I also need to write the proofs of how we get there. And the proofs aren't just going to be simple. I really need to spell out which theorems I use. So, for example, I'm using that the difference between sets, that is measurable. And I'm using the fact that this thing is measurable, that this thing is measurable, and that's how I get there. But yeah, and then we go there, and then the proof continues with doing some other things. And what I also noticed as well is that in the actual proof, they have they take a supremum here, but they don't really consider what happens if this supremum is infinite, which you could treat as a separate case, which I'm doing in the proof. So that's the benefit of doing this formalization, that you really discover all the edge cases, so that you also notice that that's something you need to pay attention to. Because when you read the proof, you might, you might also notice it when you're reading the proof, but still, it's a good way to really make sure you've got all edge cases covered. And the fact that this is now proven in Lean really means that, well, that the proof is correct, at least up to maybe not really describing all of the edge cases. Yeah. What I also noticed is that often there's a lot of, it's a bit tedious where you really need to spell out to Lean what you mean exactly. While it does, like, mathematically, it seems really trivial to do, but then you do need to tell it to Lean. So I proved here that for all x, there exists qx. Well, and then I wanted something that it says that there exists a function that for every q, that for every x provides a q. Well, and that's actually a different statement. So you, like, for when mathematicians write the proof, they actually see these things as the same thing. But then for Lean, I really need to tell Lean, okay, so I'm gonna rewrite this thing I had to this other thing so that it works. Yeah, and that just happens a lot. And then sometimes it's also just trying out which things work. So here I even use Tauto, which is, I didn't really use that much tautology. Yeah, sometimes it's just trying which basic tactic works. I could solve this here by doing simp and Tauto, but I did need to, like, for the steps before this, I really needed to specify the steps in between, which I could then do solve by simp, which is good. But yeah, that's basically it. Let's see, yeah. So it can be a little bit frustrating to do when you know something is true, but you just need, like, you need to spell out what you are going to do to the proof assistant. But in general, it turns out that it is possible to do this. In fact, it does take a lot longer than just writing down the proof. So it took me about 1 week to do this, to do the formalization of this proof. Yeah. Yeah, see if there's anything else I can say. Yeah, no, I think that's it.